the scalar product or dot product for vectors. When you multiply two vectors in 2 dimensions, what you do is you multiply the x values and you multiply the y values and add them up. In other words, if I had 1, 2 times by 3, 4, in matrices this wouldn't be allowed, right? In matrices this isn't allowed because in matrices the middle numbers have to match up. But in vectors, what we do is something very similar to what we do with matrices, is we multiply the x ones, we multiply the y values, and add them up. So the dot product of 1, 2, and 3, 4, or the scalar product, would equal 3 plus 8, 11. And the reason it's called a dot product or scalar product is because your answer is a scalar, is just a number. So in the end, you just get a number. And in 3 dimensions, you do the same thing. So if there was another 5, 6, making this bigger, you would multiply those together, add another 30, and get 41. So you multiply corresponding components and add them up. Which begs the question, why would you ever want to do that? Well, we'll figure that out in a bit. But to start off with, we've got 2 vectors, 2i minus 3j, and w equals I plus 2j. In other words, we have 2, negative 3, dot product with 1, 2. It's going to equal 2 times 1. So I can show all your work, because if you look back at your notes later, and then negative 3 times 2, and add them up, you get negative 4. In 3 dimensions, again, the idea is the same. So we have 2, negative 5, and 3, dot product with 4, 1, and negative 7. Again, I'll show the work. So it's going to be 2 times 4 plus a negative 5 times 1 plus 3 times negative 7. And we'll get 8 minus 5 minus 21. Negative 18. Pretty straightforward as far as calculating, not very hard at all. So why do we have the dot product, and where does it help us? Well, we start looking at some of the properties of dot product, and it's not super exciting. But unlike matrices, the dot product is the same if you do it forwards or backwards. You can do u dot v, it's the same as v dot u. If you have some multiple or some number in front, a scalar in front, you can do the dot product first and then multiply by the scalar, or you can multiply the scalar first by any of the 2 vectors. It will turn out the same. You can distribute the dot product, although since adding vectors is so easy, usually it makes more sense to add first and then do the dot product. But you could do the dot product twice and add your answers. And if you have a 0 vector and do the dot product with the 0 vector, everything would get multiplied by 0. Then you'd add all those zeros up, and you would get 0. Notice the difference between these 2 zeros? This one's bolded because it's a vector. This one's not bolded because it's just regular number. Okay, so far, pretty boring. A little bit more interesting. If you do the dot product with the same vector, you get the length of the vector squared. This should make sense if you think about it. Ooh, I'll do the vector 4, 3. Would you agree that it goes 4 in this direction, 3 in this direction? What's the length of that vector? 5. How do we do the length? A squared plus b squared equals c squared. 3 squared plus 4 squared equals c squared. And then you'd square root it to find c. Notice what happens with the dot product of the same one. you would get 3 squared plus 4 squared, which should equal c squared, which is the length squared of your vector. Okay, still kind of interesting, but not super interesting until we get to this result. It just so happens that the dot product is always equal to the length of u times the length of v times cosine of the angle in between them. And where this is really powerful is now we can use vectors to rearrange this and to solve for the angle between vectors. This is related to the cosine law. One of these years I'll go into a long, elaborate proof of why it works. But for today, we're going to play around with this. So what does that tell us? If the dot product is equal to the length of u times the length of v times cos of the angle between them, then if the dot product is equal to 0, that means that cos of 90 is equal to 0. And you know that those two vectors are perpendicular, which is a pretty amazing result. If the dot product is positive, that means that cos has to be positive because, again, I'll write out the formula up here again. The length of something is always a positive number. And so the only thing that's going to change whether this is positive or negative is cos of theta. In quadrant 1, cos is positive. In quadrant 2, cos is negative. So if the angle between two vectors, if the dot product is positive, you know that there is an acute angle between them. If the dot product is negative, that tells you the angle between them is obtuse. And then probably the most typical thing that you do with the dot product is rearrange the formula to get cos theta by itself, and then you can find the angle between any two vectors. Now you did angles in 2 dimensions. What's really powerful about this is we can find angles between things in 3 dimensions quite easily. Find the angle between these vectors. So we have one vector, 3, 2, 1, and another vector, 4, negative 1, 2. Try to imagine this in 3 dimensions. All right, here's my x-axis, y-axis, and z-axis. If I do 3, 2, 1, that would mean 3 in the x direction, 2 in the y direction, and then 1 up. That would be that vector. Can you imagine that in 3 dimensions? And then, if we did 4, negative 1, 2, 4, negative 1, get me to that point there. And then 2 would go up 2, so it goes up this height to there. There are those 2 vectors in 3 dimensions, and we want to try to find the angle between them. Now, if we take that new formula that we have, that cos of theta is equal to u dot v over the length of u times the length of v, and we call this our first vector, I guess it's v, and this is w. So the formula would hold, wait for it. Perfect. Save. and recovery. This means if I find the dot product, and the dot product is really easy, I'm going to get 12 minus 2 plus 2 will end up being 12. And if I find the length of w, which will be square root of a squared plus b squared plus c squared, so it's going to be 16, 17, and 4 square root of 21. And the length of v, 9 plus 4 is 13 plus 1 is 14. We can now go to our calculator and do cos inverse and find theta. First of all, we notice that the 12 is positive. So the angle between them should be between 0 and 90 degrees, which makes sense because if we look at the picture in 3 dimensions and try to imagine it, kind of looks like it's between 0 and 90 degrees. I'm going to turn my calculator into degrees. You could also answer this in radians. It did not decipher. So I'm going to do cos inverse of 12 divided by square root of 21. And instead of doing times the square root of 14, do you know when you multiply square roots, you can multiply inside? So as far as the calculator, this saves me some time just multiplying inside. My calculator, it actually doesn't matter that I close a bracket, but I want to. And the angle is 45.6 degrees. Which is an amazing result, because if you had those two lengths to try to find the angle between them, would be difficult otherwise. I guess what you could do using your old math is you could find out how long the green one is, find out how long the blue one is, then find out how long it is between them, draw that on 2 dimensions, and use your cosine law to figure it out. That seems like a lot of work, right? And the vectors makes it really easy. In fact, what the vectors is doing is basically the same idea as the cosine law, just a lot easier. Here's a new word for you. I don't know why math decided to do this, but every once in a while, they invent a complicated word that is synonymous with another complicated word. Orthogonal means the same thing as perpendicular. I don't know why we decided to add another word, because perpendicular, I think, is a complicated word enough. It's not like it comes up in everyday language and like, oh, did you mean perpendicular in the math sense, or did you mean it, that doesn't, not so much, right? Perpendicular is like, yeah, that's only math for me. But now we have another one, orthogonal. Okay, so if we want to find m, so that these two are orthogonal or perpendicular, we can use the dot product, because the dot product says if two things are perpendicular, the dot product would have to be equal to 0. And if we multiply things out and simplify this, we'd have 2m plus 3m squared minus 8 equals 0. And to solve this equation, we can either use the quadratic formula or factor. If it factors, it would have to be 3m and m. 2 and 4, outside 6, inside 4, outside positive 6, inside negative 4. Check to see that it all works out, and it does. So that means that m could equal 4/3 or m could equal -2. Given the vector u, 4i minus 3j, give a vector that is parallel to u. Anytime we're asking for parallel, the best way to solve something parallel is that it has to be a scalar multiple of 4 and -3. Choose any k value. Pick 2. 8, -6 is parallel to 4, -3. If it's not parallel, then there can't be a k that makes this work. So if I doubled the top one, but kept the bottom one the same, there will be no k that I could multiply by. I could triple the top one and times the bottom one by 381 if I really wanted to practice my 381 times table. Ooh. Maybe I'll show you a quick way to do your 381 times table up to 10. Do you like that? Okay. But first we'll finish part C, and then we'll practice our 381 times table. And we'll choose 7 to begin with, because 7 seems like a hard number. Orthogonal to u, though, we need to find something that when we multiply, or the dot product would equal 0. Now, if we have x values and y values, and if I draw out 4, -3 in 2 dimensions, 1, 2, 3, 4, 1, 2, 3, that's our vector, 4, -3. It goes 4 in this direction, down 3 in this direction. That's very similar to something you learned about lines, which is slope, right? When you think about lines, how could you tell if two slopes were perpendicular when we dealt with lines? They were the negative reciprocal, right? You remember that? And so what we can do here to find a dot product that would make this equal to 0 is we can do the reciprocal, 3 and 4, and change one of the signs from before. So if I change the -3 to +3, is my dot product 0? 12 plus -12? Yes. I could have made them both negative, and then I'd have -12 plus 12 would be 0 as well. So there's more than one right answer, but an easy way to do it is to think about doing the flip, doing the reciprocal, switching them, and changing the sign of one of your numbers. Just like in a fraction, if you had here the slope is -3 over 4, if I wanted something to be perpendicular, the slope would be +4 over 3. All right. Seven times 381. Have you been practicing your 381 times table? And be honest. Okay, good. So most people don't practice their 381 time table. How high do you usually go up with your times table? 25. Oh, that's impressive. Right? Most people only up to 1. All right? You've been working on it all week. 1 times 1. Perfect. But most people probably only know their times table up to 10, right? What's 7 times 3? 21. What's 7 times 8? 56. What's 7 times 1? 7. I'm going to write it as 0, 7. And I wrote my numbers on a weird diagonal. Now watch what happens. 2, 6, 6, 7. That's 7 times 381. Check it out on your calculator. So let's say we try a different one. Ooh, 9 times 65,384. Oh my goodness. 9 times 6? 54. 9 times 5? 45. 9 times 3? 27. 9 times 8? 72. 9 times 4? 36. 6, 5. Uh-oh, 14. I'll just add 1 over here. 8, 8, 5. 588,456. Is that 9 times 65,384? Test with the calculator. Yes. There we go. Now you know your 381 times table up till 10. Well, you could do 11 as well, right? Oh, you guys, 11 times 3, 11 times 8, 11 times 1. Does it work? But 11's easy because you can just add the number twice. Anyways, those are all number things. We want to do some more vectors. One more vectors question. Two vectors are defined as 2 plus x, 2i plus xj, and I minus 3j. Find the value of x if they're parallel. So if they're parallel, again, the first vector is 2x. The second vector is 1, negative 3. If they're parallel, then there's some value of k that makes this true. What would k have to be? K would have to be 2. If k is equal to 2, what does that make x? Negative 6. Remember, if things are parallel, one is a scalar multiple of the other. If they're perpendicular, this is where the dot product comes into play. That's the dot product, and it would have to equal 0. So solving for x here, x would have to be 2/3. Yes? Did I write down something wrong? Okay, in A, this is our first vector, 2 and x, right? And our second vector, 1 and negative 3. So to make the first equations the same, 2 would have to equal k times 1, which would make k equal to 2.